So we have all the grades. We have up to 80% of the grades. We need to grade the last homework assignment and the project and the final exam, right? So if you haven't gotten any of your grades or if you have any questions, send me email. As of now, that's the percentage of the of where the class stands, and the average and median are 89.5 and 90.5. So I guess the sort of the cutoff is that line, which is around 90. I think one of you got more than 100 with the extra credit. So that's how it looks. And so if you're in the bottom, talk to me about if there's anything we can do. And like I said, I will replace one of your grades, not counting the final exam, with the median of that particular grade. So if you did bad on one, you can bring it up to your median, not counting quizzes, because quizzes don't amount to too much either. And of course, if you've gotten everything above median, then that policy doesn't apply. So if you want to propose some kind of extra credit work, do so, because the semester is wrapping up fairly quickly. But remember that the extra credit is not meant to kill you, right? So now I'm assuming that you have other projects going on at the same time. So don't propose something of the level of I'm going to write an operating system or something, right? It's not going to be worth more than 5 points. So so talk to me before you do something, and we can figure out what is reasonable stuff you can do. Make sense? So most of you guys gotten everything else, right? All the other grades that Rob, I actually I graded yours, and I'll tell you what the grade is separately. Okay. So the last section was on security, and even though the scope of yeah, one after the other is falling. So even though the scope of security itself is quite vast, I figured I'll cover what applies to the operating system, right? So if you take a security course, some of these things may not be stressed because security focuses on the mechanisms, using encryption, all those things. But from an OS perspective, that's not so much concern. Something else is the concern, right? So we'll try to look at what those are. The slides do talk about some of the popular encryption security mechanisms, but those are in general. I mean, those you can read in a different course in more detail, right? So when you talk about security, there's a whole bunch of issues involved. So you have to. What was covered in the protection chapter was. Do you have any questions about that concept? Right. The protection chapter was talking about how you specify what the particular process or entity should, what kind of resources it should have, and what it's allowed to do, right? And the operating system would make sure that whatever policies you specify would be implemented. So the operating system provides the mechanisms, not necessarily the policies, right? Even though people tend to blame the OS for bad policies, right? And in some cases, the policies are so ingrained, it's not clear who does what, right? So for example, when you fork a new process, the process shares some stuff, right? And those are policy built into the particular operating system. So you cannot. It's very hard for you to say, I don't want to inherit certain things because the policy is also inbuilt into the operating system, right? But to the extent possible, there are some things which can be separated or something which cannot be separated out. So in terms of security is a much more vaster notion, right? It's essentially trying to protect you from something, right? And the something could be intruder who's not in the machine, right? Who's coming from somewhere. the intruder could be malicious, or intruder could be somebody who's clueless. They don't know what they're doing. So you have to protect, the operating system has to protect the machine from itself, right? So for example, if one of you started to run a program which takes all the CPU from the machine, right? And you do that because you don't know how to write good code. So you use a spin lock, and you are spinning all over the place, right? So you're attacking the machine without you knowing about it, right? So that is also something that the machine has to protect against, because regardless of what, you still are attacking the machine, right? And we'll see what the notions are in a couple of slides. And those are the notion of malicious or accidental, right? You have to protect against both those concepts, because the end result is the same. Your machine is being attacked, you can't get your work done. And however, it's easy to protect against accidental, it's harder to protect against malicious users, right? And most of the attacks come over the network. So if you have a machine which is not interacting with the rest of the world, for the most part, it's fairly secure, right? The more you let people do something, the more you allow people to bring the USB key, more you do stuff, the less secure it becomes, right? And the security has one notion which is very important, which is the notion of a trusted computing base, right? The notion says that when you build a system which is secure, you have to trust some things, right? It's not possible to build a secure system which is secure against where you don't trust anything at all, right? You have to trust something, right? So any good security work, any good security paper, any good security product will tell you, we trust certain things, and everything else can be malicious, right? And that's important notion, because you can't build a security system without the notion of what is it that you're going to trust, right? And if you look in the popular press, they don't mention that concept, the concept of a trusted computing base. But you can't prove anything unless you. So for example, if you're running on a PC, right, you have to trust that people cannot muck with the hardware, right? You have to trust that, because otherwise the software cannot do anything, right? So if you're booting from a new machine, what is the least stuff that you would have to trust? Thinking of the boot process, right? You have the firmware, then the boot sector, master boot record, and all those things. What are the things that you assume would not be messed with? Without going through detail of what the mess up is, but what do you have to trust, right? Yeah.
The loader program to load in your.
Yeah, starting from the firmware, right? You have to trust the firmware is not doing something malicious, right? If the firmware is messed up and it's running a virus, then you can't do anything. Then the boot sector has to be trusted, right? Because the operating system does not get control for those processes, right? So the boot sector has to be correct, the firmware has to be correct, and till the OS gets a chance to boot up, you don't know what is wrong with the system, right? So you have to trust them, right? So you can't build a system saying it'll be secure against boot sector fixing, right? Because you can't. Because when you change the boot sector, then whatever messed up the boot sector can lie throughout the case, right? So it can tell you that you only have one CPU when you actually have two, right? And so the question is the operating system part of the trusted computing base or not, right? And that's the $1 million question, because Microsoft was trying to push this through the trust Palladium. They keep different names for this concept, right? So one of the things that Microsoft wanted to do was work with the hardware vendors to say, if you have a trusted, I think right now it's called trusted programming module, right? If you buy these machines with a certain guarantee, right, those machines will be able to run protected software and unprotected software. You work with the hardware vendor so that when the OS boots up, you can be guaranteed that everything is secure till that point, right? If you're running in the unsecured mode, you're not allowed to do some things. You might have heard of the concept that Microsoft was trying to push. But essentially what they're trying to say is, right now in the OS, I can't trust the boot sector, I can't trust the firmware. But if you buy this machine, there's a hardware-software partnership which makes that happen. So in that particular machine, you can trust the certain things, right? There are a lot of people against that because people are afraid that that'll keep Linux and all the other open source stuff away, right? So that's the important thing that you have to realize, and that I don't have a solution from the operating system perspective, right? But that's a constant battle, like which ones do you trust and which ones you don't trust. Because if you don't talk about this, everything else is mute, right? If I don't trust your machine, if I can run as super user or whatever, then many of the things that you can do doesn't matter, because I can actually look into trying to see what you're doing, right? So in terms of security violations, the first three are considered to be the more important concepts, right? One is the breach of confidentiality, breach of integrity, and breach of availability. And all three are together considered to be security parameters, right? And none of them require you to encrypt and decrypt and all those things. These are concepts that you use to evaluate if a system is secure, right? The first one is breach of confidentiality. Says that somebody else can access your data. They may not be able to modify it, but they can have access to your data that you didn't intend them to, right? So they are able to read your data that they shouldn't have read, right? For example, if you like when the TA sent that course grades, right? Many of you could have read partially correct grades of your fellow students, and that's a breach of confidentiality, right? So there may be reasons why he did that. It was an accident, right? Regardless, there's a breach of confidentiality in that case, right? Hence, security may or may not have helped you in that context. The second notion is breach of integrity, which says that I can trust that only certain people wrote the data, right? So if there's a breach of integrity, then you should be able to log into my machine and change your grades in my spreadsheet. So the first concept says you could read my grades. The second concept says you can modify the grades, and I have no idea that you did that, right? And those two concepts are not good. They're considered to be security violations. And as you can imagine, how it happens, how you solve them, may or may not depend on you knowing anything about security, right? So imagine for the confidentiality bit, right? Going back to all the models we looked at, one of the things we said was if you're a super user, if you're privileged, you can do a whole lot of things in the system. For example, if you're running as a kernel, you can look at different kernel pages, right? You can look at what data is there. You can go into anybody's memory, right? So assume that all your programs are encrypted. We're not talking about what encryption is. Encryption basically means that data cannot be read by anybody else, right? So if I encrypt my Excel spreadsheet, you won't be able to read it, right? Let's ignore how it's done. That's the concept, right? So how would you violate confidentiality in that model without breaking the encryption and something with the operating system? You can think of a way of. So what happens is you have a Excel spreadsheet which is encrypted, right? And you as a user, let's say this is a OS, right? You do something to the operating system such that you can see what the contents are inside without breaking the encryption. Let's assume the encryption is still there, right? Can you think of a way where you can do something like this? And the answer key is the kernel mode. Right? In kernel mode, you can read any memory pages that you want, right? We also take a stab. So you can't do this when it's encrypted, right? When it's encrypted, you can't do too much stuff. But when you want to operate on this, when you open, yeah.
So if you can do kernel mode, maybe if the root password was leaked or something.
Yeah. So yeah, root password was leaked, and you go into the kernel, right? So you're running as a kernel process, right? So you can read any memory pages, right? So in that stuff, so if it remains encrypted, you can't read it, right? But all this stuff has to be unencrypted, right? Somehow it has to be unencrypted, right? We're not telling you how, but somehow it has to be unencrypted. And if you ever unencrypt it into some software object, the kernel can read it, right? So you lose all the stuff, right? So for example, if it asks for your password, right? So if there's a Excel program here, which is asking for your password, and it's reading your password, and it's storing in some memory, right? And it's using that to do some operations. So you can read what the password is, right? And this is the notion of the trusted computing base. If I don't trust the kernel can read any memory, right? So any process, if it reads a password on your screen, I can read it. I can read what you're typing, right? If I can't read your memory, I can read what you're typing, because I'm the kernel. I can do anything I want, right? So I can get all the interrupts. I can read all the context. So once a machine is attacked and your trusted computing base, if you assume that OS is safe, if that is lost, then you cannot say anything about confidentiality, because I can read any memory page. So if you ever unencrypt it to operate on the data, I can read the concept, right? Right? And so in this case, the violation happened because you assume that the operating system is secure. You assume that when you have an encrypted program, when you type in something, it's secure, right? You assume that when you log into AFS, that I haven't cracked the machine and I control the machine. If I own the machine, then whatever you type, I know, right? You type in all your password. You can have the hardest password you can think of, but when you type, I know, right? So I violated the trusted computing base, then everything fails, right? And that's pretty much one of the things where you can get through stuff in Windows. And so there's a whole bit different ways of attacking. But the point is, once the operating system is compromised, things become a lot harder, right? In terms of the hardware itself, right? Many of you are taking hardware classes, right? So if you put like probes in the CPU, and if you can figure out all the signals which are going through, right? Essentially, you can see all the data which is going between the CPU and the memory, right? It may not be cheap, it may not be trivial, but it's not that hard to build, right? If you want to build a probe which figures out all the contents which are going on the memory, right? Then you can actually essentially figure out what's going on in the system without doing anything, right? And there are ways to protect against those. They are expensive, but they can be done, right? I think IBM makes a secure core processor where if it suspects something is happening, it self-destructs, right? I think it's like $28,000 or so dollars for the processor, right? But so depending on whatever you're trying to do, those are important, right? I mean, that's the stuff of all the spy movies you see, right? I mean, you touch something, the whole thing just blows up, right? I don't think this thing like blows up like that, but essentially it self-destructs, so you can't read anything, right? So if you go really, really hard into this stuff, right, life becomes a lot harder, because if you notice any hard disk that you overwrite, you can go back and read what was erased, right? Because you leave magnetic fingerprints and stuff. So if you work really, really hard, you can read a whole bunch of stuff, right? But the key here is not protecting against the worst kind of stuff. The key is protecting against what you expect, right? So security, you don't try to build security such that it's protecting against anything you can think of. You protect against something that is reasonably there, right? You don't expect NSA to bring all their resources to find out what I have in my laptop, right? But if I was doing transactions like what Citibank does, and I'm transferring like millions and trillions of dollars a day, I would want those kind of processor. You touch something, if you can get inside and touch the CPU, then I want the whole thing to go up in flames because something is really bad, right? I mean, the banks operate on a whole lot of stuff. So security is not about making sure the system is secure against anything, because you just can't do that, because then it adds cost and everything. It's about a reasonable compromise, and that's the compromise that Microsoft does for Windows and Mac does and all those things. And sometimes those are not exactly what they should be doing, right? If the system is extremely secure such that my grandmother cannot use the computer, it is a good thing, but from Microsoft perspective, that's not a good thing. So you have to make compromises. And those all play into like what the notion of security and all those things from an OS perspective, which has nothing to do with the security, the strength of the security mechanism, right? And we make compromises throughout everything. Like most of the credit card companies these days, if it's less than $20, they don't want you to sign the stuff, right? And I still don't know what the signature means, because practically you can sign for anybody. But that's because you're mostly spending like $10, $20, and they don't really care. If you try to buy like $100,000 something, you bet they check a lot more, right? And same thing here, right? most of your machines, I don't expect you to have top secret stuff. So one of the funniest stuff is Notre Dame is moving towards more secure environments. I don't know how much it has touched you in terms of what OIT is doing for security, right? But it touches you in like some weird ways, right? So for example, Notre Dame has a notion of a firewall that they're trying to put up, which makes sure that anybody who's attacking the campus from outside would be blocked by this firewall, right? And the problem I have with all the stuff that OIT tries to do is I don't think they understand the notion of a trusted computing base, right? Because they assume that people out in the internet are bad and people who are inside are good, right? Because for walls to work, it has to separate out good from the bad, right? So the bad has to be on one side, good has to be on the other side. If that's not true, then the wall has no significance, right? I mean, if both of them are anywhere, right? And so I don't know who the bad person is, right? But I'm as bad as anybody else because I use my laptop, I go outside, because half the time I'm outside, half the time I'm inside. I'm traveling, I go use the laptop outside, then I'm coming inside, right? So what does that mean? So if you have a firewall here, right, and I can either be here or here, right? And let's say this is bad and this is good, right? So TCB would say that you have to trust these people, right? These are part of your trusted computing base. Maybe not full trust, but some trust, right? If you have no trust at all with them, then this does nothing, right? How many of you use laptops? Actually, yeah, it's pretty surprising because I was trying to plot the number of wireless devices in campus. It seems like the DOM network kind of went like this, and wireless went up like this within the last year, right? So about 30% of the users are laptop users, right? And how many of you take the laptop outside Notre Dame at all ever in your life? Right? So what are you, right? Are you good or bad, right? Depending on where you are, you're either good or bad. So you see a lot of these kind of security. So one thing, so you'll understand a whole lot about the mechanisms in a security class, but the implications of those come and haunt you because people who don't understand these concepts are making this kind of stuff, right? And so people want Windows to be more secure, right? Windows XP to be more secure. But very few people stand up and say, yes, if you make it very secure, then you have to pay the cost of security, right? Think of it as in the human sense, right? So if you want your house to be secure, you have to start locking stuff, right? And you have to start locking stuff. So you can't just say, I have a very strong steel door for my main door, right? It's a Fort Knox style door. Nothing can get through, right? Which doesn't make sense in your house because if you have windows and people can come in through and all those things, then the whole thing fails, right? So you have to make the whole thing secure. You have to believe what you can trust, right? So you have to believe that your walls cannot be breached and all those things. And none of us really want a house which is impregnable against anything. You don't want to live in a steel vault, right? But that compromise has to be figured out. And you have to understand what the OS can do and what the operating system cannot do. So if you assume that the OS is part of the trusted base, it can do certain things, it can't do certain things. And that's the stuff I want to take away from the operating system class. So breach of availability, the last one is the denial of service attack and all those things, which essentially, I don't do anything with your system, I just make it unavailable to you, right? So if I make sure that nobody can read or do anything on the machine, then I have successfully prevented you from accessing your data. So that is very trivial to do accidentally. So if you start running like 1,000 processes with which use 4 threads each or something, you can make the machine practically come down on its knees and not do anything useful to anybody else. So it's a form of security attack because you are making sure that nobody else can reach the content, right? And it's very easy to do because you can write enough processes and stuff. From an operating system perspective, you can easily solve this by saying, I'll only give you so much resources, right? I'll only give you 1/nth of the resources, right? And I won't give you anything more, right? That may be one way to solve that. But that's not very nice, because if nobody else is on the machine, you should be able to get all the resources. But if I give you all the resources, if somebody comes in, then I got to boot you out very quickly. And if I don't, then you pay the price of the stuff, right? So all three are important. All three may or may not need security, encryption, all those things. But operating system comes into all of those, because you need to understand what the trusted computing base is. You need to understand what the OS policies are doing to any of these things. And related to the breach of confidentiality is the threat of service or denial of service. So if you're on a network system, I can attack the machine, and I can use your machine to attack somebody else, not really hurt you, right? So those are more in terms of network systems. But essentially, you're doing something that I didn't want you to do, and you're destroying the system, right? And there's a whole bunch of ways you do that, and I'm not going to go into the detail of all of those. You can act as if you're somebody else. You can figure out all the operations that somebody was doing and replay them. For example, if I know what keystrokes you pressed to log yourself in, I can replay the same keystrokes, and I should be able to get inside, right? And there are ways to prevent those, and there's associated cost with those, and you make a choice, right? How many of you worked in companies where they give you this little calculator-like devices which has some numbers that you have to enter to log in? Which company is that?
It's a company down in Dallas.
Okay.
They deal a lot with like social security numbers and
Okay.
data.
From the thing, right?
No, that's to get secure access outside of the building.
Okay.
My dad has one of those, and it's actually electronic, and the code changes every so often.
Mm-hmm.
My dad has that as well. It changes every minute.
Yeah.
Every 60 seconds.
So essentially, all that it does is it has a very high accuracy clock inside, right? Which is synchronized to the central clock, and they're both running one secure algorithm, and they're both incrementing some number in a certain random fashion, right? So you have to know what the starting sequence was and what the current time is to figure out what the current code is, which is what that displays, right? So when you see the number, you have to type it in within, so it keeps changing every so often. So before it changes, if you type it in, then your server knows that you have that physical device with you, right? Because otherwise it's supposed to be that you're not supposed to guess what the number should be, because if you do, then the whole thing is lost. So it is a fairly expensive device, but it has an extremely high accuracy clock, so it can keep computing the stuff, right? And those are more secure than your password, because it's not just your password. Now you have to remember this one number, right? And if you've seen those things, those are tamper-proof. I mean, there's no screw in the back. You can't open the stuff, right? And if you try to break it open, right, they're designed to destroy themselves, right? Maybe not go up in like a lot of flame, but essentially you can't. So the security of the device depends on the fact that you can't open it and then reverse engineer the hardware, right? So if you open it, it's gone, right? So it completely shorts itself, right? But essentially those are trying to do that stuff, and those are secure. Those are expensive, right? So Notre Dame can do something like that. Give every student who comes in one of those devices. So when you go outside, you use that to log in, so we know who you are. I think those devices are like $1,500 or something per card, right? Which I'm sure none of you want to pay through your tuition, extra $1,500 to get secure access, right? So here's some of the different pictures of how the man in the middle. I don't have time to go through all the details. So essentially, for the man in the middle, if I stay in the middle of two conversations, right? Again, if it's a network situation, I'm in the middle, and if I see the traffic going through, I can hear stuff. So if I hear the password, then I can masquerade as the other person, right? So I can masquerade as the attacker, right? So if I know what your password is by listening in the middle, then I can log in as you, right? And I can also act such a way that you act like a server to somebody and they act like a client to you, right? And there are some other ways you can deal with them, and that's the focus of the security class. From a human perspective, right? How many of you use the email client other than the webmail to check your mail? So when you log in, sometimes it brings up a certificate and says, do you want to trust something, right? Do you want to trust this certificate or what have you, right? Which to the effect that this server claims it's blah, but the certificate does not match it, right? So this server claims it's imap.nd.edu, but in reality, the certificate is for something else. Do you want to trust it, right? How many of you said yes? Trust it. How many of you said no? I'm not going to use this email. I'm just going to go away, right? So he's doing the right thing, right? I don't actually do that either. I just say, okay, fine, right? And that's essentially could be a man-in-the-middle attacker, right? I mean, the certificate says the system is telling you, I'm talking to somebody, and they're not who they say they are, right? And the right course of action is you should not talk to them because they are potentially a stranger, right? But the action that most people take is you say, okay, I ignore it, right? In fact, I think like a few weeks back, the certificate expired over a Friday. And if you call OIT, their answer was, okay, ignore it, right? Right? So the right thing for OIT to say is, we messed up, we didn't pay our bills, so with the security is, our certificate expired, so come back on Monday, right? You can't use email for the next 2 days, right? But guess what would have happened if they said that, right? So, but doing so, they violated security, right? This is not a security violation; it's a social phenomenon, and that's the hardest part. So the way you breach the security is through physical means, which is taking apart the hardware, putting probes and stuff, right? Which, for the most part, I don't have to do for most of your machines, right? We don't try to keep the system so secure. We need those probes and stuff. The simple social engineering stuff is the hardest to fight, right? Where you call the OIT and they say, okay, just ignore those stuff, right? You must have stories of how you can violate even the most secure stuff easily with social engineering stuff, right? Like if somebody looks very kind of lost and they say, may I use your system to do Google Map to search something, right? How many of you would say, no, you have to, I log out, you log back in, right? If you're using one of these machines, say somebody says, I really need to know what classroom I have to go or something, right? And they look like a student, right? How many of you would say, no, I'll log out, I'll go find another machine. I can't violate the security, right? You have two who would say that, right? But for the most part, people feel like they say, okay, fine, right? They say, okay, you can use it for a moment, right? So what will happen if you let somebody do that from the operating system perspective, right? Suppose they log in, they use the system for a moment, and suppose they magically they attack and then they get your privileges, right? What can they do and what cannot they do at that instant? Anything? What?
Anything they want. I mean, if they could somehow some kind of run a little script that would be like some kind of keylogger or something, they could potentially.
No, I'm saying at the instant that they logged in as you, what can they do? Yeah, delete your files. They can do all the stuff that you can do. They can't do what you said they can do, right? They can't run a keylogger, right? Unless you can run a keylogger, right?
Oh yeah.
So the security violation means that, I mean, the operating system protects your data is toast, right? I mean, they can do whatever with your files. They can create any files. They can do anything as you, but unless they become super user, they can't do anything else. Right? They can do enough damage, but all of them are as you, not as super user, right? They have to take the next step to become super user. But for the most part, once you're in the machine, things are a lot easier, right? So remember the good, bad part, right? Once you're running in the machine, then we can do certain stuff, right? If I see somebody trying to log into the Cushing lab machines from China, right? I'll be extra vigilant. But if I see that you logged into the machine as you, then I assume that I know you're supposed to be in the class, so you're using the machine. I don't do the same level of stuff, right? But it's important to remember I don't automatically get more access. I only get access as much as you do. but life becomes a lot easier once you're inside. Like I can't run a keylogger unless you can do, right? In the class, all of you have sudo access, right? Which is a sort of a bad thing because you can elevate yourself to super user, right? Which is fine for that lab machine, but we can't do that for OIT machines. We can't give you super user, right? And so if you're trying to attack these systems, you don't usually try to attack it on the hardest part, right? You don't. The first thing which doesn't come to your mind is, let me break into the laptop, pull the hard disk out, and then I figure out what the magnetically encoded on the disk, right? The social stuff is easy enough that you can attack a whole bunch of machines, right? And there's a whole bunch of security problems, and so there are a number of different ways you can do that. You pointed out some of those stuff, which is once you're running as me, you can start running different applications and programs on my machine and get stuff. So you can run a keylogger if you're allowed to run a keylogger, right? At the least, you can run something to figure out what my password is. If the example I gave you where somebody used a web browser to install something, they don't know what your password is because they never learned your password, but they can run little programs which figure out what your password is, right? There's a whole notion of spyware, pop-ups and all those things which you'll go through in a security class. One class of attacks is the Stack Overflow, right? Which becomes interesting in our context, right? Which is if you look at the simple code, right? You're basically trying to read something in C. You don't do a bounce check for the buffer, right? You read whatever comes from RB into the buffer, and your buffer is too small. So if you read a lot bigger data, right? Then you can essentially overwrite the stack, right? Remember the stack we talked about in the beginning of the class. You have the return pointer and the data and all in the stack. So if I read right through the contents, it'll look fine inside the function, but when I return, I won't return back to where I should have. I can return to a different program, right? So if from the automatic variables, if I start writing back into the buffer, then I can make the program look like this, right? Because when I return from the function, I changed all the stack. So the stack now looks like you're calling this particular function, and buffer overflow is a very easy way to get access to your machine, right? Again, you're still running as you, not as the administrator, but now you have a foot in the door, right? And you see lots of stories about how these things are happening, and there's more graphs on that. So I'm going to skip over the boot sector. I mean, the boot, you can modify the boot sector, and that means you can't really trust anything about the particular machine. There's a whole bunch of ways of attacking the machine. So I'm not going to talk about the cryptography aspects of it, like how do you do the encryption, what are the keys, there's a symmetric key, asymmetric key, and all those things, because those are fairly involved, right? But I want you to remember what's a trusted computing base, what are the three different steps, the confidentiality, availability, and integrity. And OS gets involved in all of those, right? And it's related to the protection chapter in terms of there's a policy which decides what should happen, right? You can make the system extra secure, and then it becomes useless. So the balance of where it happens affects you, right? And this is one of the areas where people blame operating systems when they may not deserve it. And sometimes they do, but it's all a trade-off, right? So if there's anything specific, I'll try to talk a little bit about that. But for the most sense, the actual security mechanisms, you're better off studying in a different class, right? So on Wednesday, I'll go back and tie these things together. And the idea here is to say, what is it that I want you to take away from the class, right? And some of the stuff is, I want you to understand when to blame the operating system and when to blame somebody else, because that's important for what you'll end up doing, right? So I'll see you on Wednesday. And so if you haven't gotten any of your homework projects and what have you, let me know, and